Okay, right. So let's just start. So, I mean, so far we have been mostly concerned with eigenvalues of Laplacian, right? So, I mean, the spectral geometry, of course, is a much, much larger subject. So, I mean, in some sense, really, this spectral geometry is quite connected to quantum mechanics, basically, because in quantum mechanics also you see Laplacian and operators in quantum mechanics. So if you notice the kind of relation between the spectral geometry and quantum mechanics, then you also notice that there is a relation between quantum mechanics and classical mechanics. I mean, they are not so, I mean, they are kind of related through some principles like correspondence principles, semi-classical approximation. It comes in many different forms and ways, but the idea is that in some limit, in some regime, quantum things should correspond to classical. So classical things should be first order approximations of quantum effects. Anyhow, so if you notice the relation between quantum mechanics and classical mechanics, so this is kind of, I mean, this is a very vague. I mean, this arrows doesn't mean anything. I mean, this is kind of vague principle. There should be some relations between the two. I'm not going to tell you what, and it's not very clear either. There are some relations, at least. But if we believe that the spectral geometry is quite related to quantum mechanics, simply because there is Laplacian here and there is Laplacian in quantum mechanics, then we should expect that there should be a relation between spectral geometry and classical mechanics too, in some sense. And in fact, there is. There are many connections again, but one of them is there is some sort of principle that's good to maybe have in mind. So the idea is that on the quantum side, we are looking at kind of energy levels and Eigen functions. That correspond to these energy levels for the Hamiltonian. So these two gadgets. Now, what are the corresponding things on the classical mechanics side? So on the classical mechanics side, we can say these energy levels are lengths of closed orbits of the system. So lengths of periodic orbits, if you want. Periodic orbits. And eigenfunctions correspond to just the periodic orbits themselves as geometric entities. So periodic orbits. So this is a kind of very general principle. It's kind of good to have this in mind, like that. Of course, energy levels of what? Well, I mean, here we are talking about Hamiltonians, of course, right? Hamiltonian of a quantum system. So we can think of it as H as usual. I mean, H equal to P2. So we are looking at one particle, maybe P2 over 2m plus V, right? So this V, I mean, this can be formulated over any Riemannian manifold. This makes sense over any Riemannian manifold. But P is basically, I mean, in this case, so let me just write the end result. This is really equal to h bar squared over 2m. This h is Planck's constant, and then there is Laplacian here. In physicists write minus Laplacian, but because they take the negative Laplacian, we took the positive Laplacian from the beginning. So this is correct one. So don't think. And plus v. So this v is a potential function, all right? Well, okay. I mean, so this is your Hamiltonian. So this is like what we have been discussing so far was just about this Laplacian, right? We didn't have v. V for us was equal to 0. That's one thing. We should allow v to be non-zero in general. And there is this very important h also. We put h equal to 1. And that's a very bad mistake, actually. Well, it's not a mistake for what we did, but I mean, it's very important to let h as a parameter and let h change and see what happens to your formulas. This h is a kind of control parameter that a lot of things can emerge by writing formulas by having h in mind. So we completely bypass these two issues so far. I mean, we just look at v equal to 0 and h bar equal, and also m. We took m equal to half, if you want. So all these things, I mean, m is not that important, but h is important eventually. So if you have this, this is the Hamiltonian operator. So this gives you. So I mean, okay. So you want to solve this equation h of phi equal to e phi. Let me write it as. So obviously, this is immediately gives you this E or this energy level. So E, like in good cases that we also consider if you are over compact space or your potential is not growing too fast. Well, it's not growing too slowly, I should say. If it's growing too fast at infinity, that's good because it's acting like a barrier at infinity. So it's a kind of confining potential. Then then it's like you're almost like in a finite domain, and then the spectrum is going to be finite, as we discussed. But in general, this spectrum can be continuous. But in this case, let's assume this is discrete, and then you have these energy levels. So that's good. And you know this phi I, E I, phi I. So now lengths of periodic orbits. Well, I mean, what orbits of what? Well, I mean here, I mean you can think of you have a Hamiltonian, also classical Hamiltonian on phase space. So this H is this classical Hamiltonian. So again, by the same formula, but I just write it by little p over 2m. So this is like h of p and q, if you want, plus v of q. So now this time, this is a function, Hamiltonian function in classical mechanics on the phase space, right? So this, as you know, it gives you a vector field, Hamiltonian vector field. And then this gives you a one parameter flow. So you get a flow. So immediately gives you a dynamical system on, so assuming that this H is time independent, immediately gives you a time independent dynamical system on your manifold, and you want to think of periodic orbits of that. Yeah, this is on T star. This is on T star. Yeah. But somehow now I'm going to go back to M again instead of T star. So, okay, so this is a flow. So I mean these concepts periodic orbits, lengths of periodic orbits are kind of defined. But now what we discussed was the case b equal to 0, as I said. And h bar equal to 1 and m was equal to half. In this case, we know that the periodic orbits for this energy functional is just closed geodesics. I mean, its trace on the manifold is just closed geodesics, right? So, what does it mean? In that case, so this principle, this very, very general principle, then has a very special case, which is we want to focus maybe on, which is eigenvalues of Laplacian and eigenfunctions of Laplacian corresponds to what? So eigenvalues of Laplacian. Now, this in some sense should correspond to lengths of closed geodesics. So closed geodesics. And eigenfunctions of Laplacian. By the way, we didn't discuss eigenfunctions at all in this course so far. I mean, there's like more than half of a spectral geometry now is about eigenfunctions, but we forgot, completely neglected that. Well, I mean, you can do only so much, right? So, and then eigenfunctions. Of Laplacian, they correspond to just closed geodesics. Closed geodesics.
A question.
Yeah. So yeah, exactly. So that's a kind of principle we want to pursue now. I mean, it's a very non-obvious fact because I mean these eigenvalues. These are defined, I mean, eigenvalues of some operators, some unbounded operators, positive operators like Laplacians. I mean, they're very hard to calculate, and these closed geodesics also very hard to calculate why there should be kind of relation between the two. And what is the relation even? I'm not even saying what the relations are. I mean, you're just saying there should be some relation, but what is the meaning even of this statement? It's not clear, right? So it's very, very vague. I mean, you have to be aware. It's something completely in the air now. I mean, totally vague. And eigenfunctions of Laplacian, okay, also, I mean, why they should, in some sense, you can imagine in what sense these closed geodesics should correspond to eigenfunctions of Laplacian. I mean, this is one of them is function, the other one is just a curve, closed curves on the manifold. So these are very, very different kind of objects. So to make a connection between the two, this is a kind of very, very daring statement. And so we have to do something, right? I mean, so we'll try. Okay. Yeah. Yes, there was a question.
So earlier on we had seen a version of this statement where we were working on tori and then periodicity of the eigenfunction implied that they were related to closed geodesics. But I mean, how does this work in like non-symmetric spaces?
Yeah. On non-symmetric spaces, that's what we are going to get at. Yeah, gradually we have to get at this. Yeah, it's not a easy thing. I mean, so even for symmetric spaces, for manifolds with non-constant curvature, it's a highly non-trivial statement. So we will see that yeah, there are different ways of formulating the connection. Yeah. Yeah, we'll see, but we have to gradually kind of approach that. Okay, so now one case. So I mean, the question again is not that these objects are very, very different. Also, the method that you're going to relate them, it's different. I mean, there are different methods to say what the relation means, and we are going now to look at one of them. One method would be to look at zeta functions, some sort of zeta functions attached to these, say, closed geodesics, and then by zeros of zeta function, those zeta functions, see the eigenvalues as complex zeros of this as kind of dynamical zeta function. So that's the first approach you're going to try. We're going to try other approaches too, but that's the first approach. So because I mean the question is open on many levels, right? So I mean this is so the first idea. I mean this is, by the way, different from the one that I just discussed and the question, right? So the first idea today. So we are going to attach some sort of dynamical zeta function. Zeta function. Sort of, I mean, well, there's a classical dynamics on the right hand side, right? So we are going to attach a dynamical zeta function to spectrum of the Laplacian. So that's one method. So this is by itself is a huge, it's a long story. So we have to kind of just start from some very basic level. So the most basic level you can discuss this is on the circle actually, but that's not the way that we discussed for Torah. You know, lengths of closed geodesic spectrum. That's a different kind of. Okay, for Torah, for S1. So this is a circle of radius 1/2 pi, right? So it's a circle of radius 1/2 pi. So this is our S1. Okay. So circle, right? Now, for these geodesics, I mean, for closed geodesics, of course, I mean, even the term geodesic, you have to be careful. What does it mean? The term curve also, you have to be careful. Do you mean parameterized curves, or do you mean just the geometric image of the curve? These are different things, right? So, I mean, but kind of naively and intuitively, we just want to consider the circle as, you know, this one, like going this direction as one geodesic. So these are called primitive geodesics. So because they go only once, so primitive geodesics. Okay, so and then there is a spectrum you can attach to this. Okay, so there is another one that's going in the other direction. Right? So basically, you can say there are two primitive geodesics. Okay, so two primitive geodesics. And in general, for any manifold, I suppose you can define this geodesic spectrum or primitive geodesic spectrum. So primitive geodesic length spectrum. So basically, you can say this is lengths of all primitive geodesics. So this may happen that several different geodesics have the same length. So you have to count them with multiplicity if needed. So this is a set of lengths of closed, yeah, primitive geodesics. With multiplicity. Okay. So in this case, this set has two elements. Two elements. Now, the idea of dynamical zeta functions, it's an old idea, but in the sense of dynamics, it's done by Ruel, by David Ruel. So let me write it. So you can try an object like this. Dynamical zeta function. So let's see my notation for this. Yeah, so zeta is 1, or zeta in general. Yeah, it's unfortunate. I'm using the same notation for many different objects now. So this one, S, we can just say product of 1 minus p to the power, or e to the power minus SL, L belonging to L, belonging to the set L, which is this notation for this primitive. It's this one. Okay, so here L belongs to, this is the length spectrum. And S is a complex number. And you just take this infinite product. And in case if this is convergent as an infinite product for real part of S large enough, that's good. If it's not convergent, then okay. So, or if there are uncountably many elements here, for example, then okay. So you don't consider it. But the idea is this. Now, I would say it's better to put a -1 here actually, and I'll tell you why. But usually that's not done. At least the reference that I'm looking at is a paper by Zagier. And I'm sorry, I forgot her name. There's a collaborator paper that this example is worked out. So you can, it's a recent paper, maybe a couple of years ago they wrote. I mean, this is the kind of baby example they start. So let me tell you where this formula come from. So this is motivation is actually Riemann zeta function. Riemann. The Riemann zeta function has two definitions, right? And they happen to be the same. Of course, one of them is this product of, not product, is sum 1 over n to the s, right? But at the same time, there's an infinite product formula. This is Euler product formula, right? But this is also equal to product of 1 minus p to the minus s minus 1 p prime, right? So if you compare this, and if you forget about the issue -1 here, it's pretty much like the same thing, except that p is equal to e to the l, right? The prime number is equal to e to the l. So log of the prime numbers is the length of this geodesic. So log of P is equal to it. So this is the idea that in some geometric picture, prime numbers should be seen as closed geodesics. Prime number P should be seen in some geometric incarnation as closed geodesics of length log P. That's a kind of idea underlying these connections, one of the ideas. So this formula is totally motivated by this. Okay, so now, and it's a very general idea, it's a dynamical Zeta function. This is due to Riemann, as I said. But now in this case, it's very simple. So the thing is what? I mean, we can compute it explicitly in this case, right? Just Zeta S1. S is, there are just two terms here, right? 1 minus e to the s squared, e to the minus s. Now, so now we want to look at zeros of zeta, okay? So let's look at zeros of zeta.
I have a question.
Yeah.
Shouldn't the primitive length spectrum of this circle be 2 pi, not 1?
But I mean, I took the length of my circle as 1.
Okay.
The perimeter circle is 1.
Right, okay.
You know, I divided R by Z, not a multiple of Z, right?
Okay.
And that coefficient gives you the length. So I said that my circle has radius 1 over 2 pi, but it's yeah. So the zeros of this guy, of course, only this one. So e to the minus s must be equal to 1, and here we get what? S is equal to so multiple of pi I, right? So S is equal to 2 pi I k, I believe, yeah. So k belongs to right, k belongs to Z. Yeah, so yeah, we have all these complex roots of the zeta function. Now, the general idea is that this should be related somehow to spectrum of the Laplacian. The spectrum of Laplacian we have calculated already. We know what it is. So let's see what the spectrum of Laplacian is. What is Laplacian in this case? D2 dx2, this goes from L2 of S1 to itself, right? So 0, 1. So what are the Eigen functions in this case? So Eigen functions are e to the 2 pi I and x, right? These are the Eigen functions. So these are the Eigen functions, and okay, so if we twice differentiate it, we are going to get, as we did many times already, 4 pi squared n squared, where n belongs to z. So there is a multiplicity here. So we have got 4 pi squared n squared, so multiplicity is 2 for n bigger than or equal to 1, and is 0 with multiplicity 1. Okay, so what's the relation between these guys and those guys? Yeah, so the roots, I mean, here, like, I mean, if you look at roots, roots are appearing like twice because this is a like a power 2 here. So these are multiple roots. And somehow we are supposed to multiply these things together to see the actual spectrum. So the connection between roots of zeta and the spectrum is in this level. So I don't know how to push this further, but I don't want to push it further because it's a kind of very simple baby example. But you can see that there is some connection between roots of zeta and the spectrum of the quantum problem or Laplacian. Free particle moving on the circle without any interaction force. So that was one idea. That's one idea. So I'll go back to this, but then so maybe so can we do this in general? So I think that it would be a good example to try to do this in general. So so maybe a kind of exercise would be like this. Let's push this to n-dimensional flat tori. Push this to Tn flat tori. Again, well, I mean, we have geodesic length spectrum. So maybe let's, I mean, we have one connection, but let me just see what is involved in this case. I just take this. So this Tn is equal to Rn over Zn, or Rn over gamma, actually. Gamma a lattice. Okay. So this is a torus, n-dimensional flat torus. So as I discussed before, these geodesics on the flat torus correspond to lengths of the lattice themselves. So this is geodesics. I mean, closed geodesics. I mean, okay, so let me put it like this. What's the name? We called it length spectrum. So primitive length spectrum of this Tn is equal to this length of x. I mean, where this is Euclidean length, where x just belongs to gamma, right? So you look at, I argued that if you have a closed geodesic here, you can lift it to Rn on the projection map, right? Lift it to Rn. So you have to choose a point, and then it's going to be a straight line. But then, because this is a closed geodesic, you come back, and then you end up, and the difference between the two, it should be a lattice point, because they end up at the same point, right? So the difference between the two should be lattice point. So in this way, you get the correspondence between these lengths of lattice points in Rn and these primitive closed geodesics. Okay, so that's one gadget. And the spectrum also, we know what they are. And the spectrum of Laplacian, this one is equal to 4 pi squared.
So question, since you want the primitive length spectrum, shouldn't we restrict to lengths of x's where x's are from gamma such that there is no smaller vector in gamma such that x is the multiple of that vector?
Yeah, so for primitivity, yeah, that's true. Yeah, because I said primitive. Yeah, I mean that's this is indeed that's quite correct. Yes, I mean, and x is different from say nx prime or x prime belonging to gamma, or n different from 1. Because we want it to be primitive, because it's conceivable that indeed in this picture we go like twice, because that's in the lattice, but then you're covering the same closed curve twice, so we don't want to have those. Yeah, so that's that's one complication indeed. Yes. Okay, so in this case we have got this 4 pi squared norm of y squared. Y belongs to. So this is kind of simple. Y belongs to gamma star. Y belongs to gamma star. But gamma star is the dual lattice, right? So the first relation then that we saw indeed was not between this primitive length spectrum and this. We just saw a relation between a kind of the length spectrum itself for all even non-closed, for non-primitive geodesics. I mean, so let us kind of make it more precise. Yeah, I mean that's. So we saw the trace formula. The Poisson. I mean, this Poisson summation formula implied this trace formula, which is basically Jacobi inversion formula, right? Jacobi inversion. Which was, if you remember, it was the following thing: some exponential minus. We used it many times, right? Some exponential minus 4 pi squared t norm of x squared x belonging to gamma star. So this is the spectral side, or quantum mechanical side if you want. And we have the right-hand side, which is volume of the lattice. I mean, this is the volume of the torus, really, because it's just volume of one fundamental domain, right? Divided by 4 pi t to the power n over 2, and then we have a similar sum. Okay, y belongs to gamma star. Y belongs to x. Exponential of minus norm of x squared. I mean, yeah, I use norm. Maybe I just be consistent. Norm of x squared. I believe this is over 4t, right? Yeah. Okay, so maybe to be consistent by notation, I better use this notation. Yeah, I think that's better. And here I've got, okay, so y and y belongs to gamma. X belongs to gamma, sorry. Okay, now the set that we are summing over in a sense is not a primitive length spectrum, it's the full length spectrum. So this is, you can call it geometric side, but this is over full length spectrum. And in fact, in this formula, so there's another version of this formula that you multiply by n also. So there's a double multiplication, right? I mean, so you sum over, you multiply over all n's, over all or lengths. In that case, you have covered all kind of full length spectrum. But somehow right now, I just looked at it, this one. Okay, but anyhow, so this formula is of a very different nature compared to this formula. I mean, compared to this sort of, I mean, this is not even a zeta function. This is just theta functions. So the correspondence is in terms of theta functions. It's not in terms of zeta functions. So that's of a different nature. But there is some correspondence between these objects, as you can see. So one determines the other in the sense. So, but we have to be very, very careful now because we are going to kind of more general cases now. Okay. So what I asked in the exercise was to do the analog of this formula in this case for flat tori. I mean, write the dynamical zeta function and see. You see, it's going to be complicated because we are dropping exactly those ends, I mean, those multiples. So how these things are going to be related is kind of interesting. So yeah, so okay. Right, so let's move on now to another example, which is independently of interest anyhow. So this is spectral geometry of modular surfaces. So we're going to dimension 2 now. Well, I already indicated one version for dimension 2, but let's look at just sketch. Very, very sketchy spectral geometry of modular surface. So what is it? In this case, let's recall this H. The set of all x and y, or you can say maybe complex numbers, x plus iy, such that y is positive. Okay, so this is Poincare upper half plane, right? Plane. Okay, so this is so well, I mean it's a smooth manifold, and then we also discussed a Riemannian metric for this Poincare metric, ds squared equal to dx squared plus dy squared over y squared. So this is Poincare metric. Now, this metric, okay, several things about this. First of all, let's see. Okay, so let's see. So the first question is, what are the geodesics of this metric? I mean, geodesics here. So one thing to notice is that there are no closed geodesics here. no closed geodesics. I mean, geodesics are of two types, either lines that are orthogonal to the y-axis, or circles that are orthogonal to the y-axis. Lines or circles orthogonal. Oh, to x-axis, I'm sorry. I said y-axis, to x-axis. Okay, so this is a standard, what we know. And the curvature of this space, curvature, you can compute, the curvature is going to be -1. Okay, so this is a space of constant curvature -1 is two-dimensional, simply connected and complete. And as such, it's the unique space with those properties. So I mean, this object, at first it looks like random. I mean, it looks like I just took a domain and then you put a metric on it. I mean, why this metric is so special? I mean, you can, yeah, I mean, what is so special about this object? Well, this object is very, very special because it belongs to a class of manifolds that are completely, has universal properties. So let me tell you the universal property of this. First of all, let me write it here. H is the unique. So that's important. Unique, of course, by unique you mean up to isometry, right? Because everything is up to isometry in Riemannian geometry, right? Up to isometry. So unique, okay, complete. That's a condition. Simply connected. Of course, also connected, but I don't write it, but simply connected. Riemannian manifold. I mean, two-dimensional Riemannian manifold of constant curvature -1. So this is a big theorem, right? Of constant curvature equal to -1. Okay, so you see in this constant curvature spaces in dimension 2, which are complete, simply connected, and constant curvature, there are 3 of them, right? So one of them is, of course, R2, where curvature is equal to 0. The other one is S2, where curvature is 1. And the third is this. That's it. So with these conditions, being a complete, simply connected and connected, and constant curvature, you can scale, you get 0, 1, or -1. There is no other except this. I mean, two-dimensional. There are these ones. Okay, and of course there are analogs of this in any dimension. So for dimensions bigger than or equal to 2, also we have this Rn. In this case, instead of k, you have to put sectional curvature. So this would be sectional curvature equal to 0. Sectional curvature equal to 0. This is constant sectional curvature equal to 1. And this is Rn. And this is Hn. Sectional curvature equal to -1. So you can guess how Hn is going to, you already know Rn and Sn, you can guess how Hn is going to be defined, of course, right? So Hn is just, you can just forget about complex parameters. You just say x1, xn, such that the last one is positive. Xn is positive. And metric is completely similar, so you get ds2 equal to dx1 squared plus dxn squared over xn squared. So this theorem that I mentioned here, this theorem is due to Cartan. I mean, this is Cartan's classification. So there was this big problem in 19th century to classify all the space forms, right? So this is part of this space form problem. So the idea was to classify all, say, complete Riemannian manifolds that have constant scalar curvature, sectional curvature, sorry, not sectional curvature. So at each point they are completely symmetric, and also from point to point they are completely symmetric. They are kind of business of this symmetric spaces. And if you go to universal cover of those, you get these ones. Only there are 3. So all these space forms are quotients of Rn, Sn, Hn by some discrete group then, right? So that's I'm trying to say, what I'm trying to say is that this object is kind of universal object. It's in a way actually it's much more important than Rn and Sn. There's much more going on, much more geometry, interesting geometry is going on here than Rn and Sn. That's why it was discovered much later. In 19th century, it was discovered. And this has to do with non-Euclidean geometry, of course, right? So this is a model of, meaning this was the model, as you know, they were looking for this model for 2,000 years, whether this exists or not, and eventually they found it after 2,000 years almost. Model of non-Euclidean geometry. I mean, one model, there are many models of non-Euclidean geometry. One of them is this one, which is kind of nice for what we want to do. I mean, there is also disk model, and there are Kleinberg-Beltrami models, but that's okay. Okay, very good. So now what we want to do with this, of course, now we have, I mean, this is, now we want to look at, so this is non-compact and has infinite area. So we don't want to. So let's look at some kind of, again, we discussed this before, but now we want to discuss a little more. So there is this group SL2R. Acts on H, you know, as usual, A, B, C, D, Z is equal to AZ plus B over CZ plus D. So this AD minus BC is equal to 1. That's the definition of SL12, right? So this sends H to H. So you notice that 1 and minus 1, they give you the same action. So you can divide, that's the center. So center of SL2R is equal to plus minus 1. Sorry. And then and these guys, they act the same on here. So you divide this. So this is, you get PSL2R. So acts on H. And in fact, the group of orientation preserving isometries of SL of H is this one. So that's equal to isometry plus of H. Right? That's isometric loss of H. Now there is a very important subgroup here, which is the subgroup SL2Z or PSL2Z. So, so this is called the modular group. Gamma equal to, I don't know, PSL2Z, where this SL2Z, I mean, in section on modular forms and Milnor's counterexample, we discussed this a little bit, right? So this SL2Z is the set of all ABCDs such that AB minus BC is equal to 1 and ABCD are integers. So this is a discrete subgroup. So I mean, this is inside this PSL2R. So this is discrete subgroup. Right? So now the idea of this discrete subgroup is, I mean, everything is non-abelian now, right? So the idea of this discrete subgroup is that this is in some sense the analog of Z2. So this whole situation, you should think of it as a non-abelian case of much more complicated non-abelian version of R2, I mean Z2 inside R2. This is so yeah. So for tori, for genus 0, we had this R2 and this lattice Z2 inside R2. I mean, the group of isometries by translations is of the plane is R2, and then we took this lattice, we divided, and then we got our torus. So what is the torus in this case? So if we let's divide this, let's divide H. I mean, this is not completely true actually what I'm saying. So this is not. I mean, again, this is kind of very vague because this you have to divide by another thing. I mean, so the actual thing is really quotient of. Okay, so this is not a very perfect analogy. The real analogy is this. I'm going to write. So yeah, okay. Because I mean, this is a three-dimensional object. This is a zero-dimensional object, right? It's discrete. This is three-dimensional. Here, this is two-dimensional, and this is zero-dimensional. So this is not analog of that. So to have analog of that, we should have had instead is the analog of E of R2. So what is E of R2 is the group of Euclidean motions of the plane, right? It's a group of Euclidean motions of. This is a three-dimensional group. This is O2. I mean, this is how to write it? O2, yeah. Semi-direct product with R2, right? So this is the group of rotations or non-orientation preserving rotations, and then there's a translation, right? So this is the perfect analog, non-abelian analog of this. But what about now R2 mod Z2? Well, I mean, this Z2 is acting on R2, so we are going to get this one acting on that, and then we divide, right? So use action of PSL2R in gamma on this guy H, right? And we just divide and take orbit space. Let X equal to okay, so H mod gamma. I mean, okay, I take this left notation. I don't take right notation, but you can take right notation if you want. It doesn't matter. So this is So this is the orbit space of action of gamma in this upper half plane. So to understand this space, this is modular surface. Okay, by the way, this is modular surface. So this is from the point of view of Riemannian geometry, right? In complex geometry, this is called modular curve. Because in that case, I mean, there is a complex structure in the upper half plane, right? And you're dividing by this, and these are holomorphic maps. I mean, this SL2R, this Mobius transformations, of course, are holomorphic, right? So we divide, you get a complex manifold. I mean, one-dimensional complex manifold, maybe with singularities, we have to see, but this is called modular curve. So the two things are really more or less same, but we are looking at it now from different point of view. So here we are looking from point of view of Riemannian geometry we want to look at. So that's what we want to look at. Okay, so to understand this space, we have to look at, we have to take a fundamental domain, right? Like the way we looked at fundamental domain for action of, say, Z2, for example, or gamma, right? We took a fundamental domain like that. And then this identified with, I mean, R2 mod Z2. So we do similar thing here. It's, yeah. Which one?
I guess SL2Z.
Oh, SL2Z, yes. Thank you. SL2. So now, in this case, fundamental domain. So the fundamental domain is something like this. Okay, so how is it defined? This is defined by these conditions that absolute value of real part of Z is less than or equal to 1. Oh, bigger than equal, I mean less than or equal to half, I'm sorry. Less than or equal to half. And absolute value of Z is bigger than or equal to 1. So this is outside the unit circle. And in the strip, real part of Z less than or equal to 1. Okay, there is this point I here. And there is this point rho. I mean, you just solve these equations, you get that there's rho here and there's rho bar here. So what is rho? Rho is equal to e to the, well, I mean, this angle, if you, right, if this is half, right? This angle has to be 60 degrees, so rho is what? E to the 2 pi I over 6, right? So this is cosine of 60 plus I sine of 60. That's equal to 1/2 plus I root 3 over 2. And this guy is it cannot be rho complex conjugate because rho complex conjugate is down. It's rho 2. I just write rho 2 because the angle is 120 degrees.
It's minus 1/2.
Yeah, there's minus 1/2 here, right? So how to express that in terms of rho itself? It's rho squared, right? I mean, this angle, I suppose. Under 20, yeah, it's rho squared. It doesn't matter. Anyhow, so there are these points. Okay, now, so this is the fundamental domain. Notice that this line is completely identified with, so if you look at projection map into the quotient, H over gamma, this line is identified with this because there is this map T translation, which is Tz equal to Z plus 1. Takes this to that, right? And there is also this S map, right? S of Z equal to minus 1 over Z that identifies this with that. Okay? I mean, takes this section and then puts it here. So if you kind of identify this, you're going to get a surface. So the surface that you get is going to, it's a good idea to think about it like this now. So there is one point here, rho. There is one point corresponding to I. Notice that this rho and rho squared get identified under this S map in the quotient space. So but I is just single, is I. But it's an important point. So let me tell you, I mean, there's this point and this point rho. So these are called cost points. No, conical singularities. I'll tell you why. And this is the cusp. Okay, so let's look at why this is the case. First of all, I mean, the quotient is not a smooth manifold. I mean, that's one thing we have to notice. Note 1. The quotient is not a smooth manifold. It's not a smooth manifold. I mean, it's a smooth everywhere except at rho and I. So in fact, smooth at all points except rho and I. Let me tell you why. The reason is that, I mean, the action is not free at these points. I mean, if you look at isotropic groups of this rho and I, you get groups of non-identity groups. So the isotropic group of I is, what is it? I mean, this is the set of all G belonging to PSL to Z, right? Such that the G of I is equal to I. Deserves the point, right? These are kind of, we don't want non-identity elements to be there, but there is. This group is actually Z mod to Z. You can calculate this. And the isotropic group of rho is actually Z3. So these are non-trivial. So this is different from 1. I mean, 0. And the isotropic group, I just use additive notation here, so because this is also additive. So isotropic group of rho is Z mod 3Z. And this is different from 0. So these points are actually kind of conical singularities, right? So, I mean, on these points, the manifold looks like, it's like cones at this point. And kind of, yeah, it's like a plane that's been identified with itself, but under this rotation thing. So a cone is created around here, a small cone is around here. So this is important. So, of course, so this is quite important. The second thing is that, of course, the manifold is not bounded. I mean, it's non-compact, right? That's another thing, is that this guy is non-compact. So let me write it here. 2. So note 1 is what's this one. 2. X is non-compact. That's obvious. By the way, about one, this is an example of an orbifold. So this is an orbifold, right? It's a very concrete and kind of hands-on sort of orbifold in this case. So it's smooth everywhere except two orbifoldy points, which are I and O. Non-compact is okay, but it's finite volume or finite area. It's finite area. So why is it finite area? So I mean, it looks like it's going to infinity, and you may have infinite area, but it's not, because you can compute the area actually. So area is equal to. So this is going to be basically a double integral. I mean, over the fundamental domain, right? Over fundamental domain of area form. Now, the area form we can compute is dx dy over y2. Again, this is an easy integral in this case. You can compute. Why we have that? Because in general, you know, for mg, you have this formula that the volume G is the square root of determinant of G, dx1 wedge dx. And if you work out, I mean, of course, this G now is equal to what? 1 over y2, 1 over y2, 0, 0. If you work out this, you get this area form. And this integral is elementary, you can compute. And the result is going to be equal to pi over 3, actually. This is certainly less than infinity. So it's a finite area, non-compact manifold with two singularities. It's also a Riemannian manifold because the metric goes down in some sense. So to be very precise, it's a Riemannian orbifold if you want, but that's okay. So. So since now this action of gamma reserves metric, I mean Poincare metric, that's of course preserves. It follows that this descends to the quotient. So get the metric on the quotient. Get the metric of constant curvature -1. -1 on this modular surface. This we get. Again, these 2 points are orbifoldy points, and we kind of, these are, well, experience, people who worked on these things for the first time, experience showed them that these singularities are not very important, although they are kind of play a big role, of course, overall. But now a puzzle I want to tell you, if you are interested, about this space, is that this is also as I said, it's a Riemann surface, and so here is an exercise or puzzle for you to think about. Puzzle. Exercise or puzzle is this. This quotient as a Riemann surface is a smooth. I mean, it's holomorphic actually. As a Riemann surface, I mean, you have to know the definition of Riemann surface, but I suppose you know it's a complex manifold of dimension 1. So as a Riemann surface, H2 mod gamma is non-singular. So you don't see this singularity, they go away in the category of Riemann surfaces. You don't see the singularities, but as a smooth manifold, I mean C infinity manifold, it is not smooth at rho and I. At rho I mean rho and I. Images of rho and I. Yeah. So this may sound contradictory, right? Because there is this holomorphic structure. So the C infinity structure should be part of it. How come? There is no singularity as a holomorphic space, but all of a sudden, as a C infinity space becomes singular. So you have to think about it. It's a very good puzzle, very good exercise to think about kind of some issues in quotient space theory. Okay, so that's it. Now, so why did I draw it like this? That's another issue. So it's like a, you know, like a wasp, but it's kind of very strange. Why we are kind of, the reason is that in this case, as you move up the ladder, actually the distance between these two things up there, they close, they get closer and closer. So so in H, as so the distance between, I mean, so let's take one point like say x0 and y, x0 plus iy, and x1 plus iy goes to 0 as y goes to infinity. So basically, as you move up the ladder, the distance goes to, I mean, distance you can compute, right? That's very easy. So let me give you a formula for the distance. Actually, that's very easy to compute. For example, let's look at distance along this line between A to B, for example, along the y-axis, or similar to, is the same because this is translation, right? Anyhow. So let's see distance. I mean, okay, so length of any curve is equal to integral 0 to 1 square root of dx squared plus dy squared, right? Over square root of, I would say, dx squared plus dy squared over y squared, right? This is the length of any curve, right? So if you do the calculation in this case, you're going to get log of b over a. So the distance between these things, yeah, okay. So as you approach here, your distances grow, and along this line, as you go infinity, your distance to infinity, I mean, still quite big. Although now, as you go there to the boundary, I think my formula is correct.
But dx is 0.
Oh?
Dx is 0.
Sorry?
Dx is 0 in your curve.
Dx is 0, yeah. So it comes from that formula. Okay, so yeah, dx is 0. That's in the curve. Yeah, and dy is constant, so you get that. No. Anyhow, you can compute this. That's quite easy. So So we are going to finish soon because so something left from next week now. So what we want to do now, we want to look at Laplacian. I mean, so this the reason we draw it like this is because of simple calculations about distance. Okay, now so the Laplacian of this Poincare metric delta is equal to minus y squared d2 dx2 plus d2 dy2. I mean, this follows from general formula, right? Laplacian is equal to 1 over square root of determinant of g, right? dxi, what is it? Gij square root of determinant of g dxj, is that? Does it make sense, this formula? Well, it makes sense, but is it correct? Let me check. Yeah, that's absolutely correct. Very good. Okay. So this is, I mean, of course, you see this formula, you can always write it as a kind of naive Laplacian, which would be what? Gij. I mean, summation is understood, right? You can write as Gij ddxi, right? ddxj, but that's only second order term plus first order term. I mean, first order differential term plus zero order, I mean, constant, I mean, function term. So the leading part is kind of naive Laplacian, but the thing is, this is not the tensor on the general manifold, so this is not well defined, but this is well defined. And this gives you immediately this for the metric that we have. Okay, so now the idea of spectral geometry of this non-compact space, finite volume non-compact space, is that we are going, so of course now one point is that this, you see, this delta commutes with the action of SL2Z, right? Delta LG is equal to LG delta, right? Because this, what is LG? It's kind of induced action of SL2R on C infinity of H, right? I mean, as usual. So because I mean this Laplacian is isometry invariant. So and because this this G, this SL2R acts by isometry, so this is true. This is more or less a tautology. So then it means that the Laplacian descends to the quotient. Well, I mean, it's a Laplacian of. So the way we are going now to look at the spectral geometry of this guy is to look at things upstairs, but we have to look at things that are invariant under the action of Eigen functions that are invariant under the action of gamma and have some growth properties. So let me just write it down.
So a quick question. On an orbifold, it is not completely obvious to me what does it mean that a function is smooth. So basically what you said is the definition of the function that we are going to admit, right?
Absolutely right. Absolutely. That's exactly. Yeah. We don't care to be very fundamentalist and look at orbifold, everything orbifoldy and take care of those things. And yeah, Riemannian geometry of orbifolds exists. People have developed that and spent a lot of time, but we are not going to take that route. The route I'm going to take is from this Zagier and others. It's a kind of, it looks naive, but it works. You work upstairs, you make sure that everything is kind of gamma invariant, and then there is some growth condition at infinity, and then you get a discrete spectrum in this case. So that's the approach. Yeah, that's the definition. Yeah, indeed.
So like locally, an orbifold is supposed to be like a quotient of a manifold by a finite group. So I think we could basically always use maybe a similar definition, but only locally, and then it has to be glued somehow.
Yeah,
From patch to patch.
Right. I mean, locally, I mean, what is an orbifold? Locally, it's going to look like the following data. I mean, there is an open neighborhood of 0, and actually, in this case, a finite, well, it's going to be cyclic group that acts by rotations, such that there exists a gamma equivariant map between the two. Yeah. And then these different orbifold coordinates have to be compatible in some sense. So that's, I mean, definition is not very, very difficult to come up with, but it's kind of very awkward to work with that. But yeah, I mean, at some point you have to, I mean, it looks like, but not in this case. In this case, things are going to actually work out. So we want to now look at the spectrum of delta of H, of this modular surface. What is this guy? And what they did in the paper is that they test this correspondence principle in this case, and this is related to and relation between spectrum of delta x and the zeros of Zeta function. So that's quite a long story. I mean, I'm not going to get that, but what I will just give you some. I gave you the reference, but I just give you some indication of some elements of this correspondence. I mean, for example, because for the trace formula also we need later on we need this. So we are going to first of all get a handle on lengths of these closed geodesics. So the first step is to identify a primitive spectrum here. I mean, this is always important. And the length spectrum, what is the length spectrum? So in general, there is no formula, but some elements we can find, some lengths we can find explicitly, and we can tell you what this primitive things geodesics correspond to. And then we can also look at this sort of Eigen functions here, which are related to mass forms. So a mass waveform. So this is. So I will indicate this a little bit. So that gives you a sort of flavor of this direction of the spectral geometry, because this direction is very much related to number theory, and that's what people in number theory are very, very interested in. And I suppose physics also, but I'm not very familiar with that aspect. Yeah. So I think it's better to stop now. So let me just stop the thing, and then maybe